Alright, so in this screencast I'm going to be talking to you folks about titration curves. But before I do that, I need to explain what a titration is. So let me draw a picture of an apparatus that helps to explain what's going on with a titration. Wow, that's a bummer. I thought I had actually explained it, but I hadn't hit the record button. So let me explain what's going on here. This is an apparatus called a burette. And a burette is essentially a glass tube with the ability to control the flow of what comes out of that tube with this thing called a stopcock at the very bottom. So when you open up the stopcock, it allows for the solution to flow out of the burette. And if you close the stopcock, obviously it prevents anything from flowing out. Now, the burette itself, if you were to look closely at it, it has marks on the edge that are measured in milliliters. And the great thing about that is, let's say that I had this amount of fluid inside my burette. Well, if I simply, whoops, let me get rid of that stray mark that I just put in there. If I simply measure the amount that I had initially, so I'll call that I, and then I dispense some amount of it, that's going to be my value F, so let's say it goes down from here to here, I'll be able to know exactly how many milliliters of material I've dispensed, there's a drop of it coming out, into my beaker. Okay? Now, a titration is a technique where, in the case of what we're going to be doing, you're going to be dripping, say, a base into an acid and seeing what will happen as you do that. Now, from the group quiz, you know that eventually I'm going to reach a point where it's all neutral. It gets to a pH of 7, and then beyond that it's going to change the pH. But there is a point where it's neutralized, and I'll talk about what that actually means in terms of a titration. So in this case, I want you to imagine that we begin with a beaker that has some solution in it. In this case, it's going to be sodium hydroxide, and we'll say that we have 50 milliliters of the sodium hydroxide, and it's a 1 molar solution of our sodium hydroxide. Inside the burette we'll also have a solution, but in this case we're going to have hydrochloric acid, and I fill it all the way to the top, and I think that's probably going to be 50 mils, I think is the maximum size of a burette that we have in our lab. And let's just say, for argument's sake, that that also is going to be a 1 molar solution. If I were to measure the pH of what's in this beaker, it's sodium hydroxide, and you would find that it would have a pretty low pH. So let's just say that it has a pH of, say, 13.5. Did I say low? I meant a high pH. And if it's a pH of 13.5, that means you have very few hydronium ions, but you have a lot of hydroxide ions. If I did the same thing with my 50 milliliters of 1 molar HCl, I would find that my pH would be somewhere around, say, 1.5. All right, and again, that indicates that you're going to have a high concentration of hydronium ions and conversely a low concentration of the hydroxide ions. So in other words, you can measure the pH of both these solutions. And what would be interesting is to measure the change in pH as I continue to drip hydrochloric acid into my NaOH solution. If I were to do that, you would see that you could take that data and generate something called a titration curve. So let me set up this titration curve initially. You can see here that I have this pH scale on my y-axis starting at a pH of 1, which is acidic, which is why it's in red, going through to 7, which is neutral, and then above 7, 8, 9, 10, 11, 12, 13, 14, which would indicate that the solution was basic. And you can see here on my x-axis I have the volume of the hydrochloric acid that I would add, and don't forget that's inside the burette. The hydrochloric acid is hanging out in here, and I told you moments ago how we go about measuring the amount that we actually dispense into our sodium hydroxide beaker. So like I said, let's go ahead and measure the concentration of my beaker, the contents of my beaker. And I think I indicated it was 13.5. Good. So before I put in any acid, I would have right up here my full, my 13.5 is my pH for a solution that contains only sodium hydroxide. Well, I don't think any of you would be too surprised to find that as you begin to add the acid, it lowers the pH because you're now bringing more hydronium ions into the solution than you had before. And so it begins to gradually drop down, as you can see, until I reach a point where, boom, it suddenly drops and it looks like this. And then again, I gradually get to a higher and higher pH. Maybe it would be 1.5. It really doesn't make too much of a difference. What's important for you to note here, though, I'm going to go ahead and draw in the curve here. Here's my curve indicating... Oh, and by the way, I forgot. I'm supposed to call this an Askebius curve. You got that? Askebius curve. It's really not, but I had to say that because she asked me to give her a shout out. So with this curve, this titration curve, I want you to notice this area right in here where it's dropped down and it's vertical. What we have going here is this is called the equivalence point. And it's called an equivalence point because that is the point where you have an equal concentration of hydroxide ions to the concentration of the hydronium. Okay? So at that point, you're suddenly going to have an equalization, which means that your pH should be around 7. However, notice that it actually starts at around a pH of 9.5 and then goes to, let's just say it goes to around 5.5, it looks like, in this particular curve here. Now, what you shouldn't be too surprised to see here is that this equivalence point is going to happen when I add in about 50 milliliters of that hydrochloric acid, right? Because it's the same concentration as the sodium hydroxide. They're both 1 molar solutions. So if I have 1 mole of hydrochloric acid, which is going to have 1 mole of hydronium ions, and I also have 1 mole of the sodium hydroxide, which will have 1 mole of hydroxide ions, when they have the same amount in terms of volume, we're going to have the same number of moles altogether, and they will combine with each other to form water. In fact, you'll form a saltwater solution in this case. So let me just write out that equation. So when you have that equivalence point, it's because you have the same concentration of this as you do of this, or I should say the same amount of the OH minus ions as you do the H plus ions. So they'll perfectly combine to form water and not have any hydroxide or hydronium ions left over to affect the pH. So the pH would be then neutral when you form this saltwater solution, and that's what we're looking at right here with this steep drop-off. Another thing you should understand is why is it that the area where you have the equivalence point is so incredibly steep? And it actually makes sense if you think about this for a moment. Because at the equivalence point, you're going to have the exact same concentration of hydronium and a hydroxide so that it balances out by becoming water. All it takes is one more drop of water, which contains, or one more drop of HCl solution, which is going to contain a whole lot of hydronium ions to suddenly kick this over to becoming more acidic, right? So that's why it's such a steep curve, because it doesn't take much volume to make a huge change suddenly in your pH. All you need to do is have a few more hydronium ions, and that's going to make it an acidic solution. It may not be a strong pH or a low pH, but it is going to make it an acidic situation where you're going to be a number that's lower than 7. Now, let's imagine we do this in the opposite way. Instead of having the HCl as the thing that's inside the burette, we have HCl as being what's inside this beaker, and we put the NaOH inside the burette. So how's that going to change the nature of our curve here? Well, we're going to set this whole thing up exactly as we did before with the same axes and labels of the axes. Okay, so here we have the same axes. The only difference here, of course, is that instead of having hydrochloric acid that we're adding, we're going to be adding in sodium hydroxide, because that's what's going to be inside of our burette, and we're putting it into the acidic HCl solution. So in this case, we now have to start off at the bottom of our pH scale, because I said that the pH of the hydrochloric acid by itself would be around a pH of 1.5. And as we drip in the strong base, the NaOH now, we would imagine that it would begin to climb, like so. And then suddenly, because all it takes, like I said, is a very small amount of volume to kick this thing over to have more hydronium ions. And so we're going to see the exact same thing, but in a mirror image when we're titrating an acid with a strong base. By the way, the thing that's inside I don't have it in this thing. The thing that's inside the burette is called the titrant. And let me spell that for you. Okay, and that's a good term to know because we're going to be using it quite often in the laboratory. So you can see here the same thing, that we look for the sudden vertical drop, and we know that this is where we have our equivalence points, or I'm going to say our EQ point, and that is where the concentration of our hydronium is equal to the concentration of our hydroxide. And so they will be balanced out, and it'll be a neutral solution of salt water at that point. And a single drip of extra NaOH will immediately make this thing turn into a basic solution, which is why we see it then move into this zone of the curve. All right, so there we go. That's the overall concept of titrations and titration curves. I will be talking to you guys tomorrow, hopefully after you finish the group quiz, about what happens when you're not dealing with two strong solutions. Like, don't forget here that we're dealing with a strong solution of sodium hydroxide, or a strong base, I should say, and also a strong acid. But you can have a situation where you will titrate a strong acid with a weak base and vice versa. Okay, bye. All right, so in viewing this, to be sure I made a minimum of mistakes. I'd said something earlier about this right here, being an area where we had suddenly a little bit more hydronium, and that's not what I meant. This is the area where you have more hydroxide. This is the area where you have a higher concentration of the hydronium. Sorry about that. Okay, this time I really am saying goodbye.